My research from this past year focuses on one big question. Can general relativity create habitable planets in white dwarf systems? But let's start with a simpler question. Why should we look at multi-planet white dwarf systems in the first place? All low-mass stars, like our Sun, eventually become white dwarf stars. They form from the remnants of the red giant and planetary nebulae phases. White dwarf systems are quite stable and last for a really long time. So long, in fact, that the universe isn't old enough for us to see what comes after the white dwarf stage. As for multi-planet systems, scientists are aware that a majority of discovered systems have more than one planet, like our own solar system. In a white dwarf system, the habitable zone for an Earth-like planet is very close, around 0.01 astronomical units from the star. This is because white dwarfs are much dimmer than a main sequence star, which means a habitable planet needs to be closer to get the heat and radiation it needs to thrive. A big advantage of these dimmer stars is that we have a telescope that is really good at looking at the planets around them. The James Webb Space Telescope uses infrared signals from star systems to perform transmission spectroscopy that can determine what molecules might be in a planet's atmosphere. Essentially, when a planet passes in front of its star, a bit of the star's light shines through that planet's atmosphere. When we compare the original star's spectrograph to the planet-blocked one, we can see the lines where the molecules in the planet's atmosphere have absorbed certain wavelengths of light. From these lines, we can predict if any life-indicating molecules, like H2O, CO2, and methane, exist in a planet's atmosphere. In fact, recent research shows that even a small amount of James Webb Space Telescope observing time could detect these biosignatures on planets orbiting white dwarfs. So if these white dwarf planets are so great, what's stopping us from studying them? Past research has told us that if there is an Earth-like planet in the habitable zone and another planet orbiting further out, the gravitational interactions between the planets can cause excess orbital eccentricity in the Earth-like planet that would cause a runaway greenhouse effect. This theory predicts that the outer planet energizes the inner planet, causing it to release energy through a sort of squishing, which heats up the planet to the point that its atmosphere becomes too hot to maintain habitable conditions. But don't worry, there's hope. This past research didn't include a very important factor in its simulations. Remember Einstein? Well, he discovered something really cool called general relativity that changes things. Every object has a size and density associated with it that warps this weird fabric called spacetime. When objects are sufficiently close together, this can create gravitational interactions that affect the physical movements of the objects. Remember when I said white dwarfs are small but extremely dense? That means they have a strong general relativistic pull on nearby objects, especially planets in the very close habitable zone. This effect can cause precession of the perihelion, which can in turn decouple an inner planet from an outer planet. Once these planets are decoupled, the inner planet can stabilize its eccentricity and reduce or even eliminate a greenhouse effect caused by the outer planet. This is what my research predicts. From an initial simulation of a multi-planet white dwarf system, we can see that yes, general relativity works to stabilize an Earth-like inner planet with a nearby outer planet. The light purple line shows the stable eccentricity periods of the planet when we include general relativity in our simulations. The dark purple line shows that if we forget to include general relativity, our Earth-like planet has too much eccentricity and seems way too hot, when in reality it is just fine. The next step in my research was to look at many parameters to see if general relativity is strong enough to stabilize the inner planet for all types of outer planets. Here we see the maximum eccentricity of an Earth-like inner planet with varying outer planet masses and semi-major axes. This graph shows that including general relativity is really important in our simulations because it gives us much more potentially habitable planets to look at in the future. Unfortunately, each square in this figure is a simulation that takes about 2.5 hours to complete using the highly accurate code ReboundX. So a big part of my project this year was figuring out how to run simulations more efficiently. This is where CellMech comes in. After months of coding and debugging, I was able to get CellMech to run simulations that include general relativity, which it didn't have the capabilities to do before. Now we can run our simulations quickly and still maintain accuracy. However, CellMech is a little different in that it doesn't have the capability to detect chaos, meaning if we accidentally create a system where the planets or the star collide or eject, we can't really tell. All this is to say that, henceforth, our parameters are chosen specifically to prevent this while using CELMAC. Now that CELMAC works, we can get back to the science. For multi-planet white dwarf systems, the maximum eccentricity for an Earth-like inner planet to be potentially habitable is 10 to the negative fourth power. And after running many more parameter sweeps, we see the same effect as before, where general relativity is able to stabilize an Earth-like inner planet in many cases. From this, we see that the previous research is somewhat correct. When there is a much larger and closer outer planet, general relativity does not have enough strength to stabilize the inner planet. But the smaller and further away an outer planet is, the more general relativity is able to stabilize the inner planet. Finally, we get a nice graph showing the potentially habitable parameter space for these multi-planet white dwarf systems. To wrap things up, I want to share my main takeaways. Number 1, don't forget about general relativity. It exists and can have some major effects on exoplanet systems. And secondly, white dwarf systems are great candidates for detecting life because they have long and stable lifespans, the James Webb Space Telescope is good at looking at them, and most importantly, general relativity can stabilize an Earth-like planet to maintain habitable conditions.